So let's start off with some review board questions. So this first one, a pendulum is pulled to the side and released. What is the frequency of if it passes through the rest position 0.15 seconds after it's been released? So you have to be careful with these, right? So this is our pendulum, this is our rest position, and then this is up on the other side. So it says that a pendulum is pulled to the side and released. What is its frequency? So it's saying that it takes 0.15 seconds to go there. So that's only a quarter of a period because it's going to go 0.15, 0.3, 0.45, 0.6. So our period is actually 0.6. When we went over it, we got to 1 over the 0.6. And when we went over 0.6, we get 8 as an answer. Question 2. A girl bounces off the surface of her trampoline 42 times in 72 seconds. What is the frequency of the motion? So to do that, remember for frequency, we're going to get like vibrations per second or rotations per second. But for this one, it's actually bounces per second, right? So she does 45 bounces in 72 seconds. So we just have to go 45 bounces divided by 72. And when we go 45 divided by 72, we get a frequency of 0.625. So that's how many bounces she does every 1 second, right? So D is the correct answer. When a mass on a spring passes through its equilibrium position as it oscillates, which of the following must be true? Okay, so this is that example where we have our spring fully compressed, and then we have our spring going through the equilibrium position, and then our spring when it's out all the way, right? So the net force on the spring is 0, the force exerted by the spring must be 0, and the kinetic energy of the spring is 0. So remember that here it has spring potential energy, and here it has spring potential energy. So that means all that spring potential energy is going to get converted to kinetic. So it's spring, kinetic, spring, kinetic, spring, kinetic, and it just goes back and forth, back and forth, back and forth like that. So when it's at equilibrium, the kinetic energy is not 0. That wouldn't be right. So that allows us to eliminate these two. Okay. And remember, the spring force is equal to kx. Well, if it's at the equilibrium, it doesn't have any x, right? It's right here. The spring is not compressed. It's not stretched. So yeah, the spring force is going to be 0. And if the spring force is 0, it doesn't have any net force acting on it right at equilibrium. But as it passes through, it slows down. So there's a spring force building up, building up, building up, stop. And then the spring force accelerates it again. So B is the correct answer. So we have a mass oscillates in simple harmonic motion on a frictionless surface. The mass is attached to a spring. They give us a spring constant, which is compressed at distance of 0.825 centimeters and released. What is the frequency of the oscillator? Okay, so I am going to switch to this for this one because that's too much to write with that stupid pen that shoots around. So an oscillating spring is going to be period equals 2 pi square root m over k, and we're just looking for the frequency, so we're looking for the period, so we don't need to rearrange this at all. So our mass is 12.9 kilograms, our spring constant is 4.65 times 10 to the 2 newtons per meter. Okay, so we square root that, multiply it by 2 pi, and we get our period to be 1.04 seconds. So I have to 1 over that, and I get 0.9555 hertz as my frequency. So 956. Yeah, so it looks like D will be the correct answer. Okay, and then this one here is our second last one. Which of the following apply to simple harmonic motion? The maximum speed occurs at the maximum displacement. The maximum speed occurs at the equilibrium position. So we already talked about that here, right? Here it's stopped, and here it stops. So your maximum speed is always going to be when that spring potential switches into kinetic, and your maximum speed is going to be at the equilibrium position. So this is correct. This is wrong. And the maximum acceleration occurs at the equilibrium position or at the maximum displacement, right? So when it's compressed here, right, when it's stopped, we have this big spring force that wants to accelerate it, right? So my spring force is going to be equal to ma, so that's going to have a big acceleration, right? Even though that we're stopped. When we're at equilibrium, right, when the spring is stretched out a little bit more and we're at that equilibrium position, well, there's no spring force because spring force equals kx, so there's actually no forces acting on it when it's at equilibrium position. So the maximum acceleration is going to be at your maximum displacement, not at your equilibrium position. So 2 and 3 are the correct answers. And then 6, on a planet M, the pendulum with length L has a period T, and on planet N, the period with 6L has a period of 3T. How many times greater is the gravitational field strength on N compared to M? Okay, so let me switch screens here. So on planet M, so we're dealing with period equals 2 pi square L over G. And to look at this formula, we need to, or to use this formula, we're trying to compare gravitational fields. So what we have to do is we have to isolate for gravitational field. Okay, that's the first thing I'm going to do. So we get T squared equals 4 pi squared L over G. I'll move G up top, and then T squared moves down below. So I end up with G equals 4 pi squared L all over T squared. And now what we can do is we can solve this with the numbers without numbers. We just have to look at what changes. So it says on planet N, the pendulum with a length of 6L, so we're 6 timesing our length, and it has a period of 3T. So 3T, but remember T is squared, so we have to square that value as well. So how many times greater is the gravitational field strength? Well, on top we're changing it by 6, and on the bottom we're changing it by 3 squared, which is 9. So it's going to be 6 over 9, which is 2/3, so 0.66 repeated times. So on this side it's going to change by 0.66 repeated times, or 67. I should round that properly. So my answer is D. Okay. Easiest way of doing that question. Okay. So today we're going to talk about waves. So there's 2 different ways of transferring energy from point A to point B. So one way of passing energy from point A to point B is moving a particle with mass such as a pitcher throwing the ball to a catcher. So how is that energy being transferred? Well, the pitcher does work on the ball, right? The pitcher applies a force over a distance, accelerates the ball, and now that ball has kinetic energy, right? And then the catcher catches it, and the catcher slows it down. The catcher applies work to it. So that work that was put in by that pitcher switches to kinetic, and then the work is done by the catcher to slow it down. So technically, that energy that the pitcher has is from food that they ate, right? The pitcher eats food, that's what powers us. So it's that chemical potential energy in the food that goes into the work and then goes into the kinetic energy of the baseball, and then the pitcher has to apply work to it to make it stop. And yeah, so that's one way of doing it, but that's not what we're going to talk about. In this, the second way to transfer is through mechanical waves, where the energy of an object's motion at some point A is transferred to some other point B by a disturbance in the medium. So a medium is, which I'll talk about later, is just like air. It's like something that the wave travels through. So this is another way of transferring energy. And the cool thing about transferring energy through the wave is that the actual particles don't move. If you look at these individual particles here, they're just bobbing up and down, up and down, up and down. But the wave is moving from left to right, so no actual particles are moving in this situation. So a medium is a substance the wave travels through. I have a video here that just shows Star Wars, because they're traveling through space, and space, there's no water, there's no air, there's no springs in space. So when you travel through space, there's no medium, so you wouldn't be able to hear that. You wouldn't be able to hear the ships going. There would be no explosions. There's no oxygen. They wouldn't need to bank like that. Star Wars is not very correct in terms of physics. So electromagnetic waves are caused by oscillating electric and magnetic fields. So this is the waves that we're going to study in Physics 30. So electromagnetic waves, or EMR, electromagnetic radiation, they don't require a medium, and they're able to travel through the vacuum of space. So electromagnetic waves, such as light, are able to travel through space, which there is no medium because they create their own medium. Okay, and all EMR, all light, travels at the speed of light. So these are just some terms that you need to know. Propagation is the movement of a wave through a medium. So instead of saying the wave moves, I might say the wave propagates. A peak or a crest is a wave at its highest point, and a trough is a wave at its lowest point. Wavelength is the distance between peaks or troughs, how long it takes for the wave to repeat itself. Amplitude is a maximum or minimum displacement from the equilibrium. Period is the time between successive peaks or troughs. And frequency is the number of waves per second. Okay, so these are all terms that you need to know. I'm going to draw these on the next slide. So simple harmonic motion can be represented by a sine graph, and you probably haven't learned sine graphs yet if you haven't taken Math 30, but a sine graph just looks like this. It kind of looks like a wave. So you might see this term sine graph come up. Let's move this out of the way. So we can label these things on this graph here. So let's label the easy ones first. So this is my peak or my crest. This is my trough down here, right? And then my amplitude is right here, right? And you can measure my amplitude. It's always measured from my equilibrium position, but it's either from peak to equilibrium or trough to equilibrium, and you can see that they're the same. So a wavelength is if I took, so that's the symbol for a wavelength. A wavelength is if I took the distance from crest to crest, or if I took the distance from trough to trough. Those would be the same distance. Those would be the wavelengths. Right? And then our period is the time it takes for the wave to get from here to here. How long does it get from peak to peak again? So it's the same sort of thing, but wavelength is in meters and period is in time, in seconds. So there's two different types of waves you need to know about. There's a transverse wave, and with a transverse wave, the direction of the simple harmonic motion vibration is perpendicular to the wave's motion. So this, what I showed you before, is a transverse wave. So the simple harmonic motion is the particles bouncing up and down, up and down, up and down, but the wave is going this way. So they're 90 degrees to each other. So the particles go up and down, the wave goes that way. This is 90 degrees, which is perpendicular. So that's a transverse wave. Transverse waves require a dense medium, so they're only able to move through solids. Okay, so they can only move through solids. The other type of wave is a longitudinal wave, and this is where the direction of the simple harmonic motion vibration is parallel to the wave's motion. So if you look at the individual particles, right, the particles are just bobbing back and forth. So this is particle motion, back and forth, and then the wave is moving this way. And you can see these two lines are parallel to each other, so it's a longitudinal wave. So longitudinal waves are able to travel through solids, liquids, and gases. So a place where these longitudinal and transverse waves are important are with earthquakes, because with the Earth, if this is the Earth, lots of the Earth is liquid magma. Liquid. So it's liquid magma inside of here. And that means that our transverse wave can't actually travel through there. So if there's a faults happen sort of where that magma and the crust meet. So if there's a fault right here, well, the one wave can travel through that magma, and that's the longitudinal wave, but the other wave can't and has to go around the Earth right here. So what that means is that this is a shorter distance, and what we get is we get our P wave, and our P wave is here, and this is a longitudinal wave. So because it can travel through the liquid, we get our P wave, and we get that nice longitudinal wave going straight through the source. So our P wave actually doesn't do that much damage because a longitudinal wave isn't that as devastating as a transverse wave. But next comes our transverse wave, which is our S wave and stands for secondary wave. So this one you can see there's much more grand movement and it's a lot more devastating. So you always get your primary wave and then you get your secondary wave, and it has to do with what those waves can actually move through. So longitudinal waves have two different terms. They have compression and they have rarefaction. So the compression is the wave at its densest, and rarefaction is at its least dense. So we can label this on a wave. So this is the most dense, which is compression, and this is the least dense, which is our rarefaction, and then this is another compression again, right? So if we wanted to measure a wavelength, we'd measure it from the distance from compression to compression, and then our period would be just the time it takes to go from compression to compression. So speed of a wave. What do you think affects the speed of a wave? Sorry, I gotta open up this link by clicking here. Okay, so here we have a wave, and I can make this wave oscillate, and I can make it a loose end, and I can make this a nice perfect wave, and I can make it oscillate up and down like this. So you see the speed, the wave has a certain speed, so this is the wave speed that we're talking about. So what do you think can affect the speed of that wave? Well, a bunch of things can affect the speed of that wave. Maybe what affects the speed of the wave? Maybe the amplitude affects it. Maybe the frequency. Right, maybe that would affect it. Maybe the material. The medium. I should use the right terms. Maybe the medium affects it. Medium. Maybe those things all affect it. So let's sort of test it out real quick and let's see what affects the speed of the wave. So what I can do is I can add a ruler here, and we're going to measure, let's say 6 centimeters here. So we're going to measure to the 6 centimeter mark, and we have a timer here, and we can slow things down. So this is going to be our control group, and we're going to measure from when the green part gets up there, and we're just going to measure how long it takes this wave to get to that 6 centimeter mark. Okay, so here we go. It's going, stop. Oops, shoot, missed it. Let's try that again, and go. So it's about 0.9 centimeters is how long it takes to get there, right? So let's increase our amplitude. So we'll make our amplitude way bigger. So 0.9 is sort of our ground one, our control one, and then we'll go start. I'm going to measure that. Oops, let me measure our control. I remember this being about a second. Let's try this again. Oh man, sorry about this. And go. So we'll do this. Yeah, sorry, it's about a second. I measured it wrong the first time. So I remember it being about a second to that 6 centimeters. So now when we increase it, sorry, we'll measure it again. And then we'll follow this until it gets to that 6 second mark, and we get about a second. So if we have a small amplitude, it's harder to measure with the small amplitude. We'll wait for the thing to go up. And it's about a second, right? So the amplitude doesn't make a difference. So let's go back to our control amplitude to keep that a controlled variable. And now we're going to, let's up our frequency. Okay, so we'll wait for it to go to the top. Measure this. Right? So it's about a second, right? So with a big frequency or a small frequency, it takes about a second to get there. But what we do notice changes with that frequency is, so when I have a really big frequency and I pause it, right, it looks like our wavelength from crest to crest is about 2 centimeters. But if I change that frequency, can we see 2 crests on here? Yeah, so now we have a crest about 7 and a crest about, I don't know, half right here. So now our wavelength is about 6.5 centimeters. So when we increase our frequency, we shorten the wavelength, and when we shorten the frequency, we increase our wavelength. So it looks like they have some sort of inverse relationship. So the last thing that we can test is we can change the tension in our wire. Right, so it was at high, we can have high tension, and then we can have low tension. So if we switch this to slow motion, and then there's it up top, so we're just going to follow this. We're already at a second now. I'm not going to. Yeah, so it takes longer than a second here, right? And then when we have high tension, so we're going to increase our tension, and then time it up there. Oh, that's what we were at before. So that was our second one. So as soon as we slow it down, you can see those wave particles slow down. So what affects it? The medium. So that tension in that wire, that affects it. The amplitude and the frequency don't make a big difference. But what we did see is that when we increase our frequency, we decrease our wavelength. So there's some sort of inverse relationship going on there. So the speed of a mechanical wave is independent of the amplitude, the frequency, and the wavelength. The only thing that affects it is the medium. So the denser the medium is, the faster it'll go. So this means that if you have air, which is not very dense, compared to water, which is very dense compared to air, it'll go faster in water. And the speed of sound in water is about 1,200 meters per second. but the speed of sound in air is about 350 meters per second. And that's because water is denser, so the speed speeds up. Okay, and this is our universal wave equation, where v is the speed of our wave. Lambda is our wavelength. And f is our frequency. So you can find that under waves in your data book there. So this universal wave equation is pretty easy to use. But the weird thing is, okay, we're saying that the speed of a wave equals lambda f, but if the speed of the wave does not change, how can we have a formula that relates it to wavelength and frequency, right? That's weird because we said that the speed wasn't affected by it. The speed of the wave is always the same in the same medium, right? So if I double my wavelength, then what has to happen to my frequency? Well, we want to keep this the same. We want to keep our speed the same. So if I double my wavelength, in order to keep this number the same, I have to half my frequency, right? 2 times 1/2 is going to be 1, and it's going to stay the same, right? If I 10 times my wavelength, then I have to 1/10 my frequency, and that's what we saw in there. As our one went up, the other one went down, and that's in order to keep the speed the same. Okay, so let's do a couple questions, and then that's it. Okay, let's see what we have for question. So a transverse wave traveling along a rope has a frequency of 12 hertz and a wavelength of 2.4 meters. Determine the speed of the wave. So this is the easiest question. I'm just going to do it on here. V equals lambda f. They give you a frequency of 12 hertz, wavelength of 2.4 meters, and all we have to do is go 2.4 times 12, and we get our speed of 28.8. I guess we only have 2 sig digs here, so 29 meters per second. Easiest question in the world. Okay, so another question that you might see, this was inspired by this pool party here. So a transverse water wave is produced in your still bathtub by your fingers vibrating in simple harmonic motion. So just drum beating at a simple harmonic motion at a frequency of 1 hertz at an amplitude of 0.05 meters. The speed in the wave of the water is 2 meters per second. So what is the expected distance between successive crests? Well, what they're asking for here is distance between successive crests is your wavelength, right? And then to find the wavelength, we just have to use V equals lambda f, move our f down below here, and we can find our wavelength. So it says the speed of the water waves is 2 meters per second. Our frequency is 1 hertz, so that means there's going to be 2 meters in between our successive crests. That's our wavelengths. This next one's a little bit trickier. How many wave crests will lap onto the edge of the bathtub every 10 seconds? So you need to use this frequency here. So this frequency says that it's 1 wave per second. That's what our frequency is, right? And if we want to know for 10 seconds, seconds cancel out with seconds, 1 times 10 divided by 1 is going to be 10 waves. Okay. If you increase the frequency to 2 hertz, what is the new wavelength and how many? So it's the same questions, but we're increasing our wavelength to 2 hertz. Well, it said that the speed for this first one is 2 meters per second. So what's the speed going to be when we increase our frequency? Well, it's still going to be 2 meters per second because the speed does not change. What will change is the frequency and wavelength, right? So now when we make it 2 hertz, well, our wavelength is now 1 meter. We increased our frequency, we decrease our wavelength. And now we're at 2 hertz, which means we have 2 waves every 1 second. Well, if we go for 10 seconds, 2 times 10, well, now we're going to get 20 waves because they happen more frequently. Okay. And this is another type of question. You shout the name Millhouse at a wall 158 meters away. Assuming that it takes you 1 second to hear the echo, calculate the speed of sound. So here's you shout this wave at this wall, and this says that the wall is 158 meters away. So what an echo is it bounces off this wall, and then you hear it as it comes back. So for these types of questions, when they give you a distance and they give you a time, because sound waves travel at a constant speed, we can just use v equals c over t. But you have to be careful with this because it's 158 meters there, and then it's 158 meters back. So with echo style questions, you need to double this because it's got to go there and back. So it's actually going to be 316 meters is how far the sound wave traveled in a time of 1 second. So you get 316 meters per second. Okay, this last one is a tricky one, so I'm going to go through it. So a swimmer has her head partially submerged in water with one ear above the water, the other one below. A large rock falls off a cliff, strikes the water. Her submerged air hears a sound, and then her ear above the water hears it 1 second later. Determine the distance away from the swimmer where the rock hit. Use the speed of sound as this, and use the speed of air as this. Okay. So let's do this. So let's draw a little picture of what's happening. So we have our swimmer. So this is our swimmer in the water, and we have one ear above, one ear below. So a rock falls off a cliff and splashes, and then those sound waves hit the ears at 2 separate times. Okay. Well, my rock isn't on there, but there's a rock and then those sound waves. So what we know is we know that we know the speed in air. Oops, that's off the screen. Went too far up. Yes, we know the speed in air. They told us it's 344 meters per second. We also know the speed in water. Actually, I'm just going to call it VA and VW. So the speed in the water is 1490 meters per second. Okay. And we don't know the distance in air, and we don't know the distance in water, how far away that cliff hits. Sorry, that's a little bit my glary spot. There's nothing I can really do about that. And my time, they don't give us. But we do know that it hits the water ear first, so I'm going to call that time, and then a second later in air we get it to hit the ear one. The air one hears it a second later. So we're using V equals D over T for both, where this is air and this is water. Right? But we need to find common ground between the two of them, and the common ground is a distance. Right? The distance is the same. The distance away from where the rock hit in the air and the water is going to be the same. So if we move this up top and we move this up top, what we end up getting is the distance is equal to t times v, t times t for both, and the distance is the same. So I can say time in air, velocity in air is equal to time in water, velocity in water, right? Because those two distances are the same. Now I know this, but I don't know these, and these are going to be different times, but I can use what I wrote about each of them, right? The time in air is equal to time plus 1 second, and then the velocity in air is 344. And I'm just going to leave units off for now because it just makes it confusing. The time in water is just the regular time, not the 1 second. And then the velocity in the water is 1490. So I can factor this, and I can get 344t plus 344 is equal to 1490t. And then if I subtract 344t from both sides, what I get is 344 is equal to 1490 minus 344, 1146t. And if I divide both sides by 1146, that'll cancel out that. So 344 divided by 1146, and I get t is equal to 0.300 seconds. Right? So I'm trying to determine the distance away from the swimmer. Well, now that I have my time, all that I have to do is I go 0.3 times my velocity in water, 1490 meters per second. And I get 447 meters. Right? And if I did the same thing here, but time in air is going to be 1 plus 0.3 times 344 meters per second. So if I go that 0.3 that I found and I add 1 onto it, and I times it by 344, then I get 447 meters. So either one that I use, I still get 447 meters. Okay. Ooh. That one was a doozy. Okay, so here's your homework on this wave stuff. It's not too tricky. These are the V equals D over T questions. These are the V equals lambda F questions. And if you have any questions for me, just shoot me an email and I will be happy to answer you.